welcome to today's session. I want to thank everyone for attending today. My name is Kevin Holbrook. I'm one of the application engineers here at CADimensions. One of the topics that's come up that warranted some further discussion had to do with warp problems in plastic parts. So we wanted to take a look at how our solutions could potentially affect how you approach a plastic part that could potentially have warpage issues. Today we're not talking specifically about the design aspect. I think if you Google, plastic part design, warp problems, you get a pretty good cross-section of how to do ribs and transitions between thin and thick sections and how to handle the design of a plastic part. I want to talk specifically about how we look at the plastic fill analysis and what solutions we have to affect analyzing that up front when we have the geometry intact, how we go about that next step in the process. So without further ado, we'll go ahead and get started. We're going to keep this to 20 minutes or so today. Agenda is really just outlining, defining the problem. I see the group that's online, a majority of you, are plastic mold houses or plastic part designers, understand where warpage comes from, but I want to outline the breadth of the problem so that we can focus on areas in which are important to SOLIDWORKS and our software. And then I want to talk about avoiding warp without analysis and then with analysis, and give you an opportunity at the end to take advantage of our software to give it a shot and try out the warpage. So to define the problem, really warpage is that response of the material after the process of injection, after packing the material and cooling it and ejecting it into the open air. It's the response of the plastic at that point. So we have that defined. The problem itself is very complex, simply because there's many variables that affect how a part might warp. So how do we break down those variables and understand which ones we can get ahead of in the process? When we look at the causes or the things that contribute to the warpage problem, one could be operator error, right? An operator could make a wrong decision on the equipment. The injection pressure plays a role. How do we narrow down what pressures we need to be working at and optimize the pressures that is optimal for the plastic to flow properly by reducing the stress and giving us the best opportunity to eliminate or reduce any kind of warpage that we'll have. You might have issues with a low barrel temperature that could be affecting the material viscosity. We might have issues with low mold temperature, which is not allowing the material to flow the way you would expect it to flow from one end of the cavity to the other. You might have to adjust your injection time. Speeding up or slowing down will affect how easily the material gets from one end to the other and the pressure associated with that. You might have issues with ejection. Non-uniform ejection could force the material, which is still semi-molten, to a different shape. So that might be causing the issues. Understanding any kind of temperature gradients within your mold, designing a cooling system that has uniform temperature gradients or at least optimal temperature gradients, and understanding what those happen to be. Understanding the stress that the material goes through as you're pushing it through gates and through the cavities themselves. So what are we doing to the material itself, and is it able to recover? Are we giving it time to recover? Are the gates too small and they're causing or contributing to that stress? Maybe the plastic residence time is not adequate and the material is not in the molten state that it should be for injection. Maybe you have an improper flow rate for the material. Low nozzle temperatures. All of these things could be affecting how and why a part warps. So, how do we take some of these things and at least give us some optimal settings? How do we focus on and understand, okay, which injection pressure range should we be running this material on? What is the better gate size? Is it this size or this size? What is the injection time and how does it affect the result of my part and how the part fills and how it cools and all those different factors? All those decisions are things that are being made when you're working on and commissioning the mold, and you're testing this. You're taking time to make adjustments to the process on the shop floor to commission a mold like this, and that adds time and money to the process for your customers or for yourself. So how do we get ahead of this? So let's first talk about that process without analysis. Obviously, many of you are mold manufacturers. You've got a lot of tribal knowledge internally, a lot of people that know a lot about the molding business. And I don't even pretend to be one of those people. But there's definitely a large number of elements that could affect any kind of warpage that you're seeing in a particular part. When you're in this organization, you literally can go and start to look at everything from the material, the injection equipment, the mold, the geometry, and you start to go completely through the cycle to see which elements could be contributing to an issue with warp. And then you're optimizing the elements, maybe through manual testing, maybe you do a DOE and experiment all this stuff out and try to figure out what the contributing factors are. And really, bottom line is the time and money commissioning this mold. It obviously adds to the process and the cost and so on. So, we're here to talk about how we can get ahead of this a little bit. We're talking about introducing analysis, warpage analysis into your process early on. Typically warpage is caused by, in general, uneven stress. Uneven stress caused by the cooling rate of the material. One side of the material is cooling at one rate versus the other side. Cavity pressure, the inability to have a more uniform pressure from the gate to the other end of the cavity, and how do we adjust viscosities and those type of parameters to ensure a much closer cavity pressure, then pack it out properly. Fill rates, are we filling slow or fast? And then adjusting maybe your viscosity of the material with your melt temperatures. Now I just picked four parameters to look at today. I'm going to show you how we set up and adjust those using the warpage module. And then I've set up a bunch of studies so we can take a look. And then we'll give an opportunity for you to try the software in the end and do it for yourself. So with analysis, we want to bring this early in the process. If you're a mold house and you're getting this information from your customers, why not run some of this stuff early on? Find out how manufacturable it is. If there are going to be any warping issues, what the potential mold machine requirements will be, or any defects early on in that process, all in the name of saving cost and time related to that. So we do that with SolidWorks plastic simulation. I think most of you online are familiar with our plastics tool, but may have not seen our premium tool, which I'm going to show today, which allows us to look at fill, pack, cool, and warp modules. This will do your cooling lines, your warpage, any kind of mold inserts. It also does baffles and bubblers. So we'll talk a little bit more about this as we go. So let's take a look at what we have and how easy this compares to maybe the other plastics modules that you may have seen before. Now I just created a simple bezel for the sake of today's webinar, something that's long and slender, so I'll apologize if you're a mold house and this is your type of geometry here, and not how you would do it. Again, I'm not a molder, so there's some things that baffle me as well. So plastics analysis runs inside of SOLIDWORKS. It is tied to configurations. In other words, I have the default configuration here, and I've created 4 separate studies. But if I want to create a study that's tied to the default, all I have to do is make it active and I'm ready to go. Different ways of analyzing the geometry. In this particular case, because we're dealing with warpage, how the material is flowing through the thickness of the part, we're going to use a solid mesh. At this point in time, I'm not really sure if I'm going to design the runner system or the cooling system or the physical mold plates. I just want to kind of give a first pass to what's going on here with the plastic part. So we're going to mesh this thing using whatever size geometry or element that I want to use in this case. Just trying to match the existing geometry as you see here. We'll take what accounts to a skin on the model and convert it to what we call a solid mesh. This is going to allow us to take a look inside the model to see how the flow front works within the cavity of the model itself. Now, I've created a really nice part with uniform wall thickness simply for this demonstration to look at how the parameters affect it. But this is where you're going to want the flow front to be able to flow properly through the different parts of the component itself. And the elements will affect how we can visualize that. So once I have this solid mesh created, then I can kind of work my way through some of the parameters that we discussed in my first slides here. The first thing I'm able to do is to define the material itself. Now there is a material database with over 7,000 materials in here. When you select the material, one of the things that you'll see is a chart that shows how the viscosity relates to the shear of the component, and playing on different levels of this curve data allows you to see, if I were to adjust the viscosity by changing the temperature, how I might be affecting the shear rates and of that material. Again, all of the parameters associated with this, from the melt temperature to the optimal mold temperature, min and max values for the mold and the melt, all are filled out in the material. Now, one of the things I talked about adjusting is some of those values, so I'll show you where that's done in just a moment. If I skip my way down under process parameters here, this is where I can set up my fill, pack, and warp settings. Now, we mentioned filling time and its effect on the filling of the cavity, as well as the viscosity and cooling and so on. The software actually calculates, based upon the flow rates of the material, what the estimated fill time would be to flow at the optimal rate. But I can come in here and make adjustments and say, I want a 2-second fill time or some other fill time. The optimal melt temperature is transferred over. One of the parameters that we can analyze early on is, hey, you know what if I wanted to run this at 235 for a melt temperature? What if I wanted to have my mold not on the low end, I wanted it at the high end of 80 degrees C? Those parameters can be adjusted and you can see the effect on the results from that. Same thing with the pack settings. What the estimated pressure holding time is. Again, you can do change your pressure hold, let's say from 5 to 7 seconds. And then we can also adjust our pressure profile. So this is the time for the pressure hold and the pressure that we're holding at. So the curve, so how long it holds it, when it releases it, what the hold is, and we can control that specifically so we're packing the part out properly. Now it's also going to give you an estimated cool time for the part, again, based upon some of the temperatures and thicknesses. We can now adjust the cooling. This is the in-mold cooling time. As it's sitting there, it's packed out. How long is it going to sit and cool in mold? That can be adjusted and analyzed as well. When we get to the warp settings, we're dealing with the temperature of the air after ejection, looking at that as a variable, making adjustments to that, and seeing how that may affect the information. Now, going back to the mold temperature, this particular analysis is my first run. I don't really know what I'm going to get here. Maybe I just use the optimal mold and melt temperatures, optimal fill times. I'm just taking out of the box information. But the reality is, since cooling plays such a role in the warpage of the material, that I may want to get a better handle on what my temperatures look like, and we'll talk about that in just a moment. At this point, all I have to do is specify an injection location, okay, and I can go ahead and solve. Now, when we're running the premium, we can solve them individually. I can do just flow, I can do flow plus pack, or flow plus pack and warp, and solve and get some solution for each of those. Now, I've already run this, so I'm going to flip over to what we would expect to see from an analysis. It probably takes 20-25 minutes for this simple geometry to solve this. I'm able to look at everything from the flow results based upon these out-of-the-box settings. What was the fill time? 3.17 seconds. At the end of fill, what was the pressure? You can see there's a large variation in pressure from the gate to the other end of the cavity. What is the temperature at the end of fill? I can even do things as simple as doing cross sections, so I can start to look across the thickness of the part. What is the temperature at the end of fill? And that could start to work my way down the process, working my way into pack, where I can take a look at, okay, after we've packed this out, what's the pressure? You can see I wasn't able to pack this out very well with the max at the gate being 14.41 and the other end of the cavity being only at 2.1 with the time that we had. What is the temperature at the end of pack? I can go ahead and analyze, and you can see the temperature somewhere between 187 and 218 for the material at the center core. Looks like we do have glass transition on the exterior, but we do have some molten state at this point. And then warpage. Warpage is the premium module. This will allow you to see sink mark profiles, how much of a sink can be expected. It will allow you to see the residual stress of the part. So this is the molded in stress. As the material is being fed into the cavity, the stress that is created for that process, how is that affecting things? And then the quenching, the thermal stress. This is the stress from the cooling process. I can look at this in particular directions. In this case, I'm looking this component of Y to see how this thing is potato chipping. Not so bad, but I can get a magnitude of 0.27 millimeters. I can adjust the deformation scale on this thing. You can see a little bit more of the potato chipping effect and how this thing is going to curl. And I can also take a look at, through animation, a little bit of the shrinkage and how the ends one comes up from the other. We do have tools to measure and evaluate each of this. So I've kind of just taken out of the box stab at, okay, here's what I got, here's what I'm looking at. Now the process becomes very simple from here. I can go in and start to duplicate the study, and I'll just hit this little button here. We'll duplicate the study. We'll call this web demo here, and we'll duplicate this. Essentially what this is going to do is automatically create the configuration with the name that you created and copy all the plastics parameters over. So now I can come in here, change my melt temperature. I can adjust this to a different melt temperature. I want to see, well, what if I held the mold at 70 degrees? What if I changed my fill time to 2 seconds? And I could go ahead and analyze those results. Now, one of the things I can do is duplicate the study multiple times and create all the studies up front. And then what I can do is run this with what we call the batch manager. Now, the batch manager just allows me to go to the location where all of these studies are, okay, and I can create them all as a batch. I can say, you know what, for this one, I want you to run the warp. And I create this list of studies that we want to run all at one time. And what will happen is I can just run them over the weekend or overnight and really get a good look at what's going on. Duplicate study is going to allow me to do that. So that's exactly what I did here is I went ahead and made adjustments from one to the other. As I adjusted those fill time parameters, viscosity parameters, temperature parameters to get a good look at how it might be affecting my warpage. Now you can see in the first one our warpage was 0.27 millimeters in the Y. You can see at the second one, which I actually filled a lot faster at a little higher temperature on the material. You can see I have a little more warpage, probably due to the cooling on the part. And I could do this over and over and over again as many times as needed. Now, since cooling plays such a big role, one of the other opportunities that you have with the Plastics Premium is to start to get a better idea of what the cooling on the part actually looks like. So if I just open up this solid mesh here, this is the mesh for the part, you're going to notice something a little bit different here when this thing loads. In this particular case, I've actually modeled in the cooling channels as well. Now this is nothing more than sketches in SOLIDWORKS giving an identification to the diameter of the cooling channels and the direction in which the coolant flows, as well as meshing out a series of plates so we can take into account how efficiently that material is taking in the coolant temperatures as well as taking in the heat from the plastic part. So some differences that you see here is I still have my polymer, but now I can also identify my coolant. There's a coolant database where I can select, in this case I just use water. I have a mold material database where I can select the mold material. Again, we're dealing with heat transfer, and because the temperature is probably playing the biggest role in the warpage, I want to make sure I've designed a cooling channel that's going to cool this thing properly. I can now identify the pipe. What is the inlet? What is the outlet? What is the flow rate, temperatures? All of that can be identified. So some very simple, easy tools to get a little bit more information about the results. And what this really provides us is a much more accurate look at how this thing is cooling through the process. So I can start right at the first step as the cooling temperatures at the end of fill. You can already see the ends of the part aren't getting cooled as well as the rest of the part. So I might want to find a way to get some cooling at that location. At the end of pack, what are we looking at for temperatures? Okay, with this cooling design, you can see I was able to pack everything out a little bit better, a little bit higher pressures. I would assume that the warpage is going to be a little bit better as well. For the cool piece of this, we can get a good look at total part cooling time, temperature at the end of cool, cycle temperature, average heat flux, heat load, taking a look and optimizing that process as well. And in the end, I can take a good look at, once again, the displacement due to the stress and cooling in that Y direction. And this happens to be my least amount of warpage. So I went really fast here. I've identified a few things. I'm just going to go back here. Things like the cooling rate. We can modify the cooling lines, the cavity pressure. We can adjust the hold times, the fill rates, which will affect our pressure. And then our melt temperatures, adjusting the viscosity, all in the name of trying to predict the mold machine requirements and manufacturability of this part with that particular material. So I want to thank you for attending today, but I want to also give you an opportunity to give it a try. I know a half hour is not a lot of time when it comes to seeing this thing in action, and I kind of feel like benchmarking is the way to go. You know, get a part that you know you've seen warpage on before and run it through this process and mimic what it's been doing. So what I want to offer you is, if you send me an email, kevin@CADimensions.com, I will get you a trial of Plastics Premium. That Plastics Premium trial will run for 30 days. During that process, I just would ask that you commit to just some phone calls that we can help you learn a little bit more about the software, how to set it up, how to get going with the software. Another opportunity that I want to offer you folks is the ability to do a plastics consult. If you didn't feel you had the time to take the trial, what you can do is let me know at kevin@CADimensions.com that you want to do a consult. You can send me over the part. I'll ask for some process parameters or what information that you have, and we'll run through and we'll set up the analysis for you, and we'll come in and present the results. Just to give you an idea of how this might match up with what you have today. There is also the opportunity for a plastics hands-on test drive. If this is something you're interested in, again, let me know. We can set up a hands-on test drive. You're going to come in, we're going to use our own parts and be able to step you through the setup of a project. Now, I've overly simplified this thing today. What I wanted to make clear is that if you do some of this parameter work up front, you're going to be way better off and further along in the process when it gets to that point where you're looking at the machine and the machine options. You're going to know approximately where you're going to be. You're going to be able to do some optimization early, and you're certainly going to help that process quite a bit. So let me know at kevin@CADimensions.com if you wanted to get any of those, the trial, the hands-on, and we'll go from there. So I want to thank you for attending.
Don't forget to check us out on YouTube, Twitter, Facebook, and our blog for more great content by clicking on the links in the description below.